Hi, welcome to 9.1, the ellipse. So we're going to talk about 9.1, 9.2, 9.3. We're talking about what we'll call conic sections. And I have this diagram, and I hope it comes through. I hope you can kind of see it here. I brought the screen down so you didn't have the bad glare from the board for this part. What I want to get through with conic sections. Now, conic section, this by the way came from Wikipedia and it is cited on there, and you can read the notes. You can see it there as well. Three types of conic sections: the ellipse, parabolas, and hyperbolas. So you have the case like this, where you have your plane that intersects it. A plane is a two-dimensional surface, like a piece of paper if it wasn't curved. Where it hits the cone, creates, in this case, is creating a parabola. If it's parallel to this one of these angled sides of the cone. Now, in this case over here, you have the plane that intersects it, goes all the way through, or down here. These are ellipses. And in ellipses, you get, this is a circle, where this is more of the oval-shaped ellipse, but circles are ellipses. Then if you have your plane parallel to the axis of your cones, like if you imagine a line going through the center, it's parallel to that, you get two of these curves. These are not two parabolas, these are hyperbolas. So those are the three cases: parabolas, ellipses, hyperbolas. So I'm going to raise this up now. Okay, the algebraic definition of conics. A conic section described by an equation of the form ax squared plus cy squared plus dx plus ey plus f equals 0. Now I want to point out they won't have all these, some of these values will be 0, so they're not all going to be, they're not going to have too many values in there. This is the general form for conics, where at least one of the two coefficients a and c is not equal to 0. It's a parabola if a times c is 0. That means one of the two is 0, but they're not both 0. It's an ellipse if a times c is positive, and it's a hyperbola where if a times c is negative. So it's possible, though, that d could be 0, or e could be 0, even f could be 0. So I mean, it is possible that not all of them are going to be 0, so that's okay too. But that's the general form of a conic section. Let's talk about the geometric properties of a conic. First, an ellipse, and that's what we're talking about in this section. An ellipse consists of the set of points in a plane for which the sum of the distance d1 and d2 to two foci, that's a plural of focus, is a fixed constant. Let me draw a little picture of something like that. Here are the foci. Now, an ellipse is a collection of all the points such that the distance, let me change colors here. Here's d1, d2, so that the distances d1 and d2 to two foci is fixed, the sum of those distances. Let's pick another point. Call this D3 and D4. So what we're saying is that D1 plus D2 is equal to D3 plus D4. The sum of the distance from any point on the ellipse to the foci is going to be a constant. So the sum of these distances to the foci from that point would be constant. And that's an ellipse. A parabola consists of the set of points that are the same distance d from a line called the directrix and a point not on the line called a focus. So here's your focus. This is the directrix. Okay. So a set of points of the same distance d from a line and the focus. So what we're saying then is that this distance D, this is D, call that D1. It's the same distance. Whereas the distance from this focus to that point should be the same as this. I didn't quite draw this right. Maybe this should have been a little wider. D2, D2. But that's the idea, is that this distance would be the same. This distance is the same. Okay, the next one's hyperbola. Consists of all the set of points, consists of the set of points for which the magnitude of the difference of the distances D1 to, start over again. Hyperbola consists of the set of points for which the magnitude of the difference of the distances D1 and D2 to two foci is fixed. Let's draw a picture of that. Foci 1, foci 2. So pick a point, like here's a point. Call this D1, call that D2, and pick another point. Call that D3, call this D4. Now, the absolute value of D1 minus D2 is equal to the absolute value of D3 minus D4. That's the relationship, or that's what defines a hyperbola. Okay. So in this section, we'll be talking about ellipses, and 9.2 parabolas, 9.3 hyperbolas. So we're going to go further on into ellipses now. So first of all, an equation of ellipse centered at the origin, so at 0, 0, would be x squared over a squared plus y squared over b squared equals 1. In this case, x has the major axis. That means it's wider horizontally than it is vertically. The x-intercepts are located at a0 and negative a0, and the y-intercepts are located at 0b and 0, negative b. The foci are located at c and c0 and negative c0, where a squared minus c squared equals b squared. And actually, there's a typo there. That should be a squared minus b squared equals c squared. Okay. So the major axis is the line segment extending from one extreme point of the ellipse to the other and passing through the two foci. So the major axis goes through the two foci, or you can say the foci are on the major axis. Vertices are the two endpoints of the major axis. And the minor axis is the line segment that also passes through the center and is perpendicular to the major axis. So the major axis is the longer one, minor axis is the shorter one. And since we're talking about the case that x has the major axis would be wider and the minor axis would be shorter. Okay, it spans the lengths of the major and minor axes. Hang on, let me go back to this. The minor axis is the line segment that also passes through the center and is perpendicular to the major axis. And I should say, it spans the other two extremes. See that? The other two extremes. Leave it like that. Okay. Now, it's possible that x or y can have the minor axis, but not both. Most of the ones we see, I'd probably say maybe like 60% of the ones we see will have x having the major axis just because our minds are probably more used to seeing something like that, so it's kind of perpetuated. Okay, a standard form of an ellipse. So we saw the one where it's centered at 0, 0. Here's a standard form. Assume a and b are fixed positive numbers where a is bigger than b. The standard form of the equation of an ellipse centered at HK with major axis of length 2a and minor axis of length 2b is x minus h, where h is the x-coordinate, over a squared, plus y minus k, where k is the y-coordinate, over b, y minus k squared over b squared. And that's if the major axis is horizontal. Now notice what's changed in the second one. A, which is bigger than b, as we defined it, is under the y portion, so it's x minus h squared over b squared plus y minus k squared over a squared. And that's if the major axis is vertical. So having a vertical major axis means the bigger number is below the y. Having a horizontal major axis means the bigger number is under the x. So important distinctions. In both cases, the two foci of the ellipse are located on the major axis, c units away from the center, where c squared is a squared minus b squared. So let's do some examples here. Find the center, the foci and vertices of the ellipse that the equation describes. Okay, so we have x plus 3 squared over 9 plus y plus 1 squared over 16 equals 1. Now, given that 16 is bigger than 9, this must have a vertical major axis. Our a squared is 16, so a is 4. B squared is 9, so b is 3. Now where's the center of this? Well, it should be x minus h. So think of that as x minus negative 3, so h would be negative 3. Y minus k, so it'd be like y minus negative 1. So k must be negative 1. So our center is going to be at negative 3, negative 1. And if it helps to see a little picture of this, we can draw a picture. There's the center. Now A is 4, that's our major axis, so we're going to go up 4 from this location. So 1, 2, 3, 4. Go to green for that. And down 4 from this location. These are the vertices. So this vertex is located at negative 3, 3, and this is at negative 3, negative 5. So we have vertices at negative 3, 3, and negative 3, negative 5. Now our b-axis says, the minor axis we have b, we're going to go to the right 3, 1, 2, 3. It's right there at 0, 0. And to the left 3, oh, I'm sorry, it's not up here, it's down here. It's down here at 0, negative 1. Okay. Then over here to the left 3, down here again, and that's located at negative 6, negative 1. So we could draw our ellipse now. So it looks circular, but it's not. It is a little more stretched this way than that. I probably need to start coming up like this here. Okay. So we have the center. We have the foci. Oh, we don't have the foci. We have the vertices. Let's get the foci. So the foci are located at C units away from the center. So it's C equals a squared minus b squared. So c squared equals 16 minus 9. C squared is 7, so c equals the square root of 7. So that means if I go up, square root of 7, now square root of 7 is approximately what? .65. So we can go up 1, 2, 2.65 units. That's going to end up being at -3, 1.65, and then go down 2.65, up 1, yeah, there, and then down. I didn't draw this, didn't scale this consistently. That's probably the problem here. And that's going to be at -3, -3.65 for our foci. And that's the approximation there. So we have our vertices, our center, and our foci. And again, major axis is vertical, so the foci are on that major axis. I mean, they're always on the major axis, so they're vertical. Okay. Let's look at B here. X squared plus 2y squared minus 6x plus 16y plus 37 is 0. So we're going to do a little bit of algebra first. So we do x squared minus 6x plus blank plus 2y squared plus 16y plus blank equals -37, and move the 37 over. This would be x squared minus 6x plus the blank plus 2 times the quantity y squared plus, let's see, that's going to be 8y plus the blank equals -37. I forgot to do my plus blank, plus 2 times the blank for the second case. So half of -6 is -3. -3 squared is 9. So adding 9 to both sides. And half of 8 is 4. 4 squared is 16. So I'm going to add 2 times 16. So this will become x minus 3 squared plus 2 times the quantity y plus 4 squared equals, so it's -37 plus 9 is -28 plus 32 is 4. Now in an ellipse it should be equal to 1, so we'll divide all these parts by 4. We have x minus 3 squared over 4 plus y plus 4 squared over 2 equals 1. And that's our equation for the ellipse. Now our a in this case, the bigger number is below the x, so a is 4, that's going to be under the x, so it's going to have a horizontal major axis. Because the first thing to ask is where's the center? Our center will be at 3, -4. 3, -4. Wrong way. Okay, so 3 -4 puts it right about here. Now a squared is 4, so a would be 2. So come 2 units this to the left. And that's going to be at 1 -4. and then 2 units to the right. That's going to be 5, negative 4. Our vertices are located at 1, negative 4 and 5, negative 4. Now we have to find our foci. Just to complete this, I want to have fun with this. B squared is 2, so B is the square root of 2, or approximately 1.4. So we come up 1.4 and we go down 1.4. Okay. There's our ellipse. We need the foci. So the foci are going to be located where? We have c squared equals a squared minus b squared. So c squared is going to be equal to 4 minus 2, so c squared is 2. C is the square root of 2, approximately 1.4. So from our center at 3, negative 4, we go to the right 1.4 units. And right about there. So this is going to be located at 4.4, negative 4. Go to the left 1.4 units, so 1.4. And that's going to be at 1.6, comma, negative 4. So our foci are located at 1.6, negative 4, and 4.4, negative 4. Okay. Okay, feel free to pause that. We're going to move on to example 2. I'm going to clear the board. So the next one, a little easier. We just have to graph it. We've been graphing them, but we have a nice grid here to graph on this. So we have, let's see, so sketch the following graph of the ellipse, and determine the coordinates of the foci. So first of all, our center will be at negative 5, negative 2, because it should be x minus h, y minus k, negative 5, negative 2. So if I ask you, will it have a vertical axis, major axis or horizontal, what are you going to say? You're right, vertical. Why? Because of 16 under the y versus 4. So our a squared is 16, which means that a is 4. So we're going to go up 4, down 4, and then we have to go, for the minor axis, b squared is 4. So b must be 2. So we're going to go to the right 2, and to the left 2. And here's our ellipse. And then we have to find the foci. So our c squared is a squared minus b squared. C squared equals 16 minus 4. C squared equals 12. C equals the square root of 12. Well, it's just the positive. I mean, I guess we could say plus or minus because it goes up and down. So C is plus or minus 2 times the square root of 3. Okay. And let's see, that's about 3.4. So C is approximately plus or minus 3.4. So we're going to go up 1, 2, 3, 3.4 is up here. Down 1, 2, 3, 3.4 down is that far. So our foci are going to be located at -5 plus 3.4 comma -2, -5 minus 3.4 comma -2. No, I'm sorry, I did that backwards. -5 comma -2 plus 3.4, -5 comma -2 minus 3.4. So we could say foci are located at -5 comma 1.4 and -5 comma -5.4. There we go. And that is the graph of our ellipse, and that is the location of the foci. In each of the following problems, we only have one, that's a generic heading. An ellipse is described either by picture or by properties it possesses. Find the equation in standard form for the ellipse. I included a graph on this one just to help us put it together. So vertices at 5, -1, and 1, -1. So we have 5, -1, and 1, -1. Those are vertices, which means it must have a horizontal major axis. Now, what's the center between those? What's the midpoint between 5, -1 and 1, -1? Well, that'd be 5 plus 1 divided by 2. -1 plus -1 divided by 2, 6 halves comma -2 halves, so it's 3 comma -1. That's our center. Our minor axis is equal to 2, and that's 2b then is equal to 2, so b must be 1. So we're going to go up 1, down 1. So that's what our ellipse would look like. So what's the equation of the ellipse? It's going to be x minus 3, the x location for the center, plus y minus -1, the y location for the center, over something each equals 1. It opens horizontally, so the major axis, the a squared is going to be down here. What's our a? What's the distance from 3, -1 to 5, -1? A must be 2. So a squared is 4. 4. B is 1, so b squared is 1. So our final answer, x minus 3 squared over 4 plus y plus 1 squared over 1 equals 1. That's it. Okay, our last concept from this section, we have eccentricity of an ellipse. Given an ellipse with major and minor axes of length 2a and 2b respectively means that major goes with the first one, minor goes to the second one. The eccentricity of the ellipse, often given by the symbol E, is defined by E equals C over A, which of course C is defined to be the square root of A squared minus B squared. So find the eccentricity and the lengths of the major and minor axes of the following ellipse. So it's 5x squared plus 8y squared equals 40. If I divide both sides by 40, x squared over 8 plus y squared over 5 equals 1. So a squared must be 8. So a would be the square root of 8, where a is 2 root 2. B squared is 5, so b must be 5. So our major axis will have the length 2 times 2 root 2, or 4 times the square root of 2, where the minor axis is going to be 2 times the square root of 5, which is 2 root 5. Now let's find the eccentricity, but we need c first. C squared is equal to the a squared minus b squared. So it's going to be 8 minus 5, which is 3. So c would be the square root of 3. Our eccentricity E is going to be c over a, which is the square root of 3 over the square root of 5. No, I'm sorry. Over 2 times the square root of 2. And that would work out to be approximately 0.6124. Okay. And that'll do it for 9.1. Okay, send me your questions. Thank you.